Hey everyone, we're just waiting one more minute while people filter in here. Okay, well, I think we'll get started. So it's my total pleasure to introduce Assistant Project Scientist Tom Beucler. Tom got his PhD in 2018 at MIT in atmospheric science with Carrie Emanuel and Tim Cronin. His thesis was focusing on how cloud self-aggregation under radiative convective equilibrium using spectral techniques. And that's a hot topic, and that work won the Rosby Award at MIT for best thesis. So this is probably going to embarrass him, but I have to say Tom's just a great scientist and colleague. He came to us as a postdoc in 2019 and then figured out the nuts and bolts of machine learning in record time and solved some really important problems that you'll hear about today. What he won't tell you about is how much other stuff he's doing, so I need to. But I wanted to mention that in the US, he's helping us run this US CLIVAR working group new webinar series on emerging data science. He's been very active in selecting speakers. Runs his own weekly webinar. It's my favorite meeting, and which is attracting a lot of great young researchers exploring machine learning for climate across Oxford, MIT, CMWF, UCSD. In Europe, he's waking up really early to mentor another big group of German PhD students that are funded by a big European Research Council grant on machine learning you might have heard of, led by Veronica Ehring and Pierre Gentin. All just to say his technical expertise in this topic is in huge demand. He's writing invited book chapters, giving invited seminars, etc. And then meanwhile, on the side, he's still working on radiative convective equilibrium and actually just put out a cool paper with a couple of postdocs at MPI Hamburg where they've made an analogy between surface tension physics and large-scale patterns of aggregation in the tropics. So anyway, I hope you're getting the picture, and sorry for embarrassing you, Tom. But I just wanted you to know that landscape before diving into the technical work today. Tom loves collaborating and has got broad interest, and part of why he stepped up to give an ESS seminar is to discover some new interfaces with our department. So if you find the work interesting, please engage with Tom after the seminar. I can attest only good things come from that personally. But without further ado, Tom, take it away. Thank you.
Thank you so much, Mike, for the kind introduction, and good afternoon, everyone. So after Mike's generous introduction, I thought it was my turn to thank him for being such an expert and open-minded advisor who also keeps attracting very curious and hardworking students and postdocs in his lab at UCI, and I'm so happy to be working with most of them. And my talk would not be the same without all of their advice. And today we'll share, as Mike said, some of my recent progress towards developing physically consistent and data-driven models of convection. And I would like to thank Alex Gunther for inviting me today and Elliot McCollum for co-organizing the seminar series, as well as all the co-authors of the work I'm presenting today, some of which are listed at the bottom of this slide. So from a climate science perspective, there are three motivations for this work. The primary motivation is that the largest uncertainties in our long-term climate projection still come from clouds, and the main culprits are boundary layer maritime clouds and cirrus clouds. More specifically, climate models fail at representing the effect of fine-scale cloud and turbulence on climate because most climate models still use a very coarse grids with empirical models of clouds and convection, which distorts the multi-scale interaction between climate, convections, and clouds. Fortunately, thanks to recent computational advances, we are now able to run global simulations with a grid that is fine enough to explicitly simulate deep cloud systems. However, because of computational limits, we are only able to run such simulations for a short period of time. For instance, 1 year, which is much less than the 100-year or the 1,000-year simulation we need to make informative long-term climate predictions. In parallel to the development of global cloud resolving model, progress in optimization has improved machine learning algorithm In this talk, I'll generally define machine learning algorithm as any algorithm learning tasks from data without being explicitly programmed to do so. So this progress in optimization has improved machine learning algorithm to the point where they can be trained on these very high resolution simulations like the one I showed you in the slide before to accurately mimic the effect of deep cloud systems on the climate. And to make things a little more concrete, I will show the setting we use in our lab. In our lab, we mostly rely on climate simulation that use the super parameterized community atmospheric model. And it's a specific and convenient type of high-resolution climate model where the multi-scale nature of atmospheric thermodynamics is explicitly represented via the combination of, on the left, a pretty coarse climate model, very similar to traditional global climate models, and on the right, an interior model, which is an expensive cloud-resolving model that explicitly resolves and simulates the effect of fine-scale turbulence and clouds on scale climate. And then the role of the neural network is to emulate and replace the interior model, which can make the climate model up to 100 times faster with minimal accuracy trade-off. So for those in the audience who are not familiar with neural networks, you can view neural networks as a very powerful nonlinear regression tool, taking high-dimensional inputs and non-linearly mapping these inputs to high-dimensional outputs. The parameters of neural networks are then optimized using variation of the stochastic gradient descent algorithm. And the goal of this optimization algorithm is to minimize a loss, or also named cost function, that typically measure how different the predicted output is from the outputs that we're trying to learn from data. And neural networks have been rapidly adopted by the physical science community following the demonstrated success in computer vision. Now, in our case today, the details of the neural networks I am going to present can be adjusting for the modeling task at hand, but all the neural networks I will show today take solar insolation, temperature, specific humidity, which is water vapor concentration, and surface enthalpy fluxes as inputs, and then map these inputs to how temperature is redistributed in the vertical by convection and fine-scale turbulence, and how water vapor is redistributed in the vertical by these same fine-scale processes, as well as predicting radiative fluxes at the top and the bottom of the atmosphere. So here is a movie showing the performance of such a neural network at emulating subgrid scale thermodynamics from a super parameterized climate simulation that uses Earth-like boundary conditions. With the ground truth we are trying to emulate at the top, and the predictions from the neural networks at the bottom. Convective moistening on the left, convective heating on the right. And what you can see is that the neural networks does a very good job at emulating the general patterns of subgrid scale thermodynamics minus a little bit of variability. And these really promising results that are common to now several atmospheric science labs across the world ask a very general and provocative question, which is, can we eliminate physics entirely from a model? And by that, I mean, can we avoid explicitly encoding physical knowledge in the algorithm we use to make atmospheric predictions? And below, I give another example of a very provocative result of data-driven numerical weather prediction where the entire model, including the model's dynamical core, has been replaced by a deep convolutional network. And the point I would like to make today is that while the answer is maybe we can eliminate physics for initial conditions problem like numerical weather predictions, keeping in mind that of course those deep learning weather emulators rely on physical model data when they're trained, the answer is probably no for climate modeling, which is a boundary condition problem where the physical system we're trying to model, Earth, is exposed to condition it has never been exposed to in the recent past. And the answer is no for at least 4 different problems that I want to tackle today. interpretability, physical consistency, ability to generalize outside of the training set, and sparsity of observations. So the first problem is that machine learning are typically hard to interpret. And because they are hard to interpret, they are hard to trust. So here I am showing the example of a pretty poorly trained neural networks, which when coupled to a climate simulation leads to the entire climate simulation crashing in a few days. So the question the climate modeler is going to ask is, why should I trust a model if I don't even know before coupling it to the climate model if it's going to be stable at all? And you can see that simulation blowing up with very dramatic internal gravity waves on the right. The second problem is that machine learning algorithms typically violate conservation laws. So I'm showing the residual from the mass conservation law at the top in watt per meter square, and the residual from the enthalpy conservation equation at the bottom in watt per meter square. And if the neural network was a statistical algorithm you're interested in, perfectly conserved mass and enthalpy, we should see a delta function, a quasi-delta function close to 0. But then when we, in practice, feed a batch of inputs to typical neural networks that model convection, what we get is very different. We get an entire distribution of how neural networks violate mass and energy conservation, with typical values that can be as large as 100 watt per meter square, which for the climate modelers in the audience, you know, is completely unacceptable. Even just dissipating 1 watt per meter square of mass or energy per time step is already a deal breaker for simulations that are going to be as long as 100 years. The third problem I would like to tackle today is that machine learning algorithms fail to generalize outside of their training set. So here I am showing a daily average profile sampled from the tropics of a reference climate that we trained a neural network on. And if we test those neural networks on this, if we evaluate those neural networks on this profile, including neural networks that have been engineered to conserve mass and energy, all of them fit the daily mean tropical profile of here sub-grid scale moistening pretty well. However, if you take the same networks and evaluate them in the tropics of a climate that is just 4 Kelvin warmer, that they have never been trained on, all of these neural networks, including the physically constrained one, make very large generalization errors. And this is the third central issue I want to address today. The fourth and last issue arises when we take a step back from the modeling world, where we live in a very luxurious regime where data is unlimited in practice because we can generate our own data. For context, in neural networks, I was showing you for the real geography simulation, typically uses 40 million, if not 100 million samples during training to reach the performance that you saw. And while the current global observing systems can approximate the large-scale thermodynamic state to a decent precision, which informs then the development of global climate models, the same cannot be said for the outputs of the neural networks I was talking about and the outputs that we need to parameterize subgrid scale thermodynamics in climate models. Those outputs being subgrid scale moistening and heating tendencies, which are typically residuals of much larger tendencies. And so the only way we can accurately measure them is by conducting costly and targeted field campaigns. On the left, I'm giving the example of the Eureka campaign in the Barbados. And what that implies is that to address the recurrent biases that we have in climate models, we are forced to work with very sparse and localized data to then develop data-driven parameterization of convection. And that is very challenging using traditional data assimilation techniques. So given these 4 problems, we ask, how can we remediate them and design interpretable, physically consistent, and data-driven models of convection? And more generally, this fits into the more general questions. How can we best combine machine learning and atmospheric physics? how can we find the right mix of physical and statistical knowledge to create models that will reduce our climate model uncertainty while still being trustworthy. And in this talk, I'm going to show that you can make progress towards these interpretable, physically consistent, and data-driven models of convection by first tailoring existing interpretability tools that already exist in the machine learning community to the specific task of machine learning parameterization of convection. Second, I'm going to show you that we can enforce conservation laws in neural networks, either approximately by modifying their loss function or exactly by modifying their architecture. Third, I will show how physical rescaling can help neural networks generalize outside of their training set and introduce the notion of climate invariant neural networks. And last, I will show that these climate invariant neural networks can learn more general mappings from climate to convection with very little data and facilitate transfer learning between idealized and realistic atmospheric data. And note that while in this talk we are investigating the very specific case of subgrid scale thermodynamics deep learning parameterization of convection for climate modeling, the mathematical and computational framework I will be presenting today to solve these four problems are more generally applicable to to machine learning emulators of physical processes for Earth system models or other physical systems in general. So going back to the first problem, how can we change our, how can we trust or better interpret machine learning algorithm of physical processes, in our case, for convective modeling? And to do that, we need to first take a step back and think about how interpretability is defined to begin with. And it's commonly defined as the degree to which a human can understand the cause of a decision. But for our purposes, it may be more convenient to define it as a degree to which a human can consistently predict a model's result. And today I will introduce two interpretability methods that greatly increase our confidence in our neural networks prediction. And more specifically, I will show how two interpretability techniques can be tailored to better interpret machine learning parameterizations of convection. So the first method I want to talk about today is called partial dependence plot. And what it does is that it shows the marginal effect of one or two inputs on the predicted outputs. For mathematically inclined folks in the audience, you can see a neural network as a nonlinear mapping from the input vector x to the output vector y. Then the idea is to isolate the inputs of interest, here noted as x partial dependence plot, that together with the other inputs can be concatenated to form the full input vector. And then the partial dependence function that we want to plot to make those partial dependence plots is mathematically defined as the expected value of the model's output conditionally average over inputs of interest. So now, if you're less mathematically inclined, pragmatically, all you're doing is that you're estimating the outputs of a neural network by averaging over chunks of data that have the same inputs you're interested in. And now onto the particular case of the emulation of convection. We are going to show partial dependence plots based on two physical quantities that we know are reasonable good proxy for atmospheric convection. The first one is mid-tropospheric moisture, defined as the water vapor concentration around 500 hectopascal in the atmosphere, and is known to be the fuel of atmospheric convection as it can be converted to rain. The second input we are interested in today is lower tropospheric stability. And what that measures is the difference in potential temperature between the surface and the lower troposphere, roughly 3 to 4 kilometers above your head. And that one controls if convection is allowed to occur or not, and where it occurs in the atmosphere. Will it form boundary layer clouds, like the typical clouds you see above your head in Southern California, or will it form very deep convective clouds, like the clouds you would see if you have ever been on a tropical island? And so at first, I'm going to fix the lower tropospheric stability and vary mid-tropospheric moisture and see the effect it has on subgrid scale moistening on the left and subgrid scale heating on the right. As I increase mid-tropospheric moisture, there's more and more fuel for atmospheric convection. And what you can see is that progressively, moistening and heating are both going to increase in amplitude. And now you have the typical signature of how convection occurs, for example, in a violent thunderstorm, where water vapor is transported upwards and then condenses into rain. When it condenses into rain, there's a big drying because you converting water vapor into liquid water, then fallouts. And because you're converting from the vapor to the liquid phase, you produce a lot of heat, which will end up heating the atmosphere, which is why you see this big subgrid heating on the right. Now we can play the opposite game where we fix the mid-tropospheric moisture to this very high value, and then we vary the lower tropospheric stability to see that if by increasing stability, we are able to stabilize the atmosphere. And we get results that are pretty similar to what we observe in the real atmosphere, which is the higher the lower tropospheric stability, the less the magnitude of the convection is. And note that in the paper I'm referencing below, we do not only limit our analysis to the amplitude of subgrid moistening and heating, but to the full shape of the vertical profile. As for instance, lower tropospheric stability is known to control the occurrence of boundary layer clouds. And I encourage you to read the publication below if you're interested in detail, which has been recently published in the Journal for Atmospheric Science. The second technique I want to show today is called saliency maps, and it is typically defined as a squared Jacobian of the emulated mapping. So to make it a little more visual, here it is applied to a convolutional neural network that predicts if this image is an owl or not. And if you look at the saliency map, here, it shows you the gradients that are most relevant to predict if this image is an owl or not. And what you can see is that the algorithm focuses on the eyes and the head of the owl the most. So by modifying the pixels in these regions, you're most likely to modify the neural network decision from yes, it is an owl to no, it isn't an owl. Saliency maps are directly related to Jacobians. And a particular property of deep learning is that because neural network rely for the optimization on the calculation of this Jacobian via automatic differentiation, we have very efficient algorithm to calculate the Jacobian of the mapping we're trying to emulate, defined as the sensitivity of the output vector with respect to the input vector evaluated at the value of a particular input vector. In the case of convection, a Jacobian we are typically interested in and we can obtain from our model is the sensitivity of convective moistening at every level in the atmosphere to moisture, or how humid the atmosphere is at every vertical level. So this is how it looks. And to give you a little more intuition, you can forget the unit on the axis for a second. And the horizontal axis gives you the vertical level at which we perturb moisture. And the vertical axis gives you the vertical level at which convective moistening responds as a result of this moisture perturbation. And what I find so exciting when I started working on machine learning is that with more traditional models of convection, this figure takes hundreds of forward perturbation experiments to make. So this is very, very computationally expensive to make, even with very simple models of convection. An alternative is to sit down and analytically derive the adjoint of the model to then calculate this linear response. With machine learning, because automatic differentiation is so efficiently implemented, you can automatically get that average over hundreds of inputs in just a minute, or maybe a few minutes if your neural network is very big. Now I'm going to show you that it gives you already a lot of physical intuition about the emulator you have built, and potentially the physical system you are studying if the emulator fits the real system well enough. So in our case, you can see that, for example, there's a blue diagonal. And what that means is that, for instance, if I perturb water vapor in the mid-troposphere, in response, the convective moistening is going to be decreased. And so what that means is that local anomalies are removed. So convection works like a faster version of diffusion, except that unlike diffusion, it rapidly redistributes the local anomalies it has removed to the lower atmosphere. Now, on top of physical intuition and interpretability, what we did with this Jacobian, which is summarized in the paper, is that we took two neural networks and we were trying to predict if they were going to be stable or unstable. And so on the left, we took a very good fit, a very good neural network that is stable. And on the right, we also calculate the Jacobian of a neural network that is unstable. And you can already see just visually that those two Jacobians are different. And then we showed that by coupling those automatically derived Jacobians with simple two-dimensional atmospheric dynamics, we were able to automatically derive the full stability diagram of the entire dynamical system, which in this case is an internal gravity, gives you the phase speed on the x-axis and the growth rate on the y-axis of internal gravity waves. And we can derive this diagram offline. That means without even coupling the model, without even coupling our statistical emulator to the climate model. If you have sharp eyes, you've already noticed that the unstable network has a lot of modes with positive growth rates. And so before even coupling it to the climate model, we were able to predict that it's stable. This neural network will be unstable, and you can even predict how quickly those very dramatic gravity waves are propagating outwards. Once you have that information, you can stabilize neural networks offline without having to do the expensive and time-consuming step of coupling them with the climate model. So for example, using a super-parameterized climate model data, we showed that by regularizing the inputs by adding Gaussian noise, we could eliminate all the unstable modes. And using the global cloud resolving model emulator that our collaborators at the University of Washington derived, they showed that they could stabilize a neural network by removing the upper atmospheric inputs. And then once we couple the stabilized neural networks online, we found that they ran without crashing for more than 1 month, despite being, in that case, a pretty bad fit that would only crash after a few days normally. So I hope this has shown that we can quickly adapt, tailor machine learning interpretability method to the particular case of machine learning algorithm of physical models, so we can better interpret and trust them. And now I'm going to transition to the second problem I mentioned today, which is how can we enforce physical constraints in data-driven models of convection? And in particular, how can we enforce conservation laws that we care so much for the purpose of climate modeling? In the context of a neural network model of emulation, we are mostly interested in the conservation of mass, energy, and radiation. So the first step which is a universal step whenever you want to enforce physical constraints, is to add all the terms informing conservation laws to the neural network's inputs or outputs, or at least all the terms from which you can derive the terms that go inside the conservation laws. Once you've done that, there are two ways of enforcing constraints in the literature, mostly two ways. The first option is to enforce conservation laws via soft constraints in the loss function. And to do that, there's a lot of literature on the topic. You can introduce a penalty for when your model violates conservation laws, which is similar to a Lagrange multiplier. So instead of writing your loss function as only a performance loss, for example, the mean squared error, you reserve some weight of this loss function to penalize the network whenever it violates conservation laws. The problem is that's only approximate, and approximate conservation, like approximately following conservation laws, is often not enough from a climate modeling perspective, where we really don't want spurious mass or energy sources and sinks in our statistical emulator. And so what we developed was a relatively general new method to enforce conservation laws to within machine precision by augmenting the neural network with what we called constraints layers. And so for those of you who do machine learning, I'm going to give the details in the next minute. You start with a standard neural network mapping the input vector to an output vector of total length p, but instead of outputting the full vector of total length p, you output a vector of length p minus n, where n is the number of constraints, exact constraints you know, for example, conservation laws. And then you calculate the remaining components of the output vector using fixed constraints layer. Now the trick is that instead of doing this as a post-processing step, you concatenate this vector with the direct outputs within the neural network. So this is all coded within the neural network. And then you optimize the neural network using the entire output vector so that the final weights, parameters of your neural network explicitly depend on the constraints you want to strictly enforce, here conservation laws. So now onto the results. I'm first going to show that if you enforce constraints in the loss function, there is a trade-off between how well you enforce physical constraints and the general performance of your algorithm. So on the y-axis is mean squared error, which represents the skill of a network. A higher mean squared error is bad, a lower mean squared error is good. And the first step that is very important when we do deep learning is to check that we beat a multiple linear regression baseline. It's a really important first step because there's no point in deriving complicated machine learning algorithm if a simple linear regression performs better than the complex emulator you're trying to build. So in our case, it does. It's justified. Note the logarithmic scale. So there's a real difference in scale between this point and this line. Now, what we found really surprising is that then if we evaluate how much the algorithm violates conservation laws, the neural networks is so bad that it performs almost an order of magnitude worse than the linear regression when it comes to following conservation laws. Fortunately, if we increase the weight assigned to the physical constraints in the loss function more and more, the resulting algorithm follows conservation laws more and more closely, which is reassuring. But it comes at a cost, and that cost is that the neural network performs worse and worse. Meanwhile, if we apply our conservation laws using exact fixed constraints layer, we're able to get a very competitive performance. Our performance is almost as good as a completely unconstrained neural network while enforcing conservation laws to within machine precision here in our case. So that is a result we were really excited about. But now that leads to a third problem, is that even when we physically constrain the neural network, because the problem we're interested in is very high dimensional and has much more than the degrees of freedom than the amount of conservation laws that we know about the system, even when physically constrained, neural networks fail to generalize. And here is the example from the introduction, where both the loss and the architecture constraint neural network violate conservation law. They don't violate conservation laws anymore, but they make very large generalization errors when they evaluated in a climate that's warmer than the climate they were trained on. And so then we went on a quest to better understand the failure modes of our statistical emulators and why they fail so bad at generalizing. And our first idea was to break the model even more to make sure we could better understand those failure modes and then possibly remediate them. So what we did is we defined a very ambitious generalization experiment, which is that we train and validate our neural networks on a cold aquaplanet simulation. And then we warm that simulation by 8 Kelvin, which for any climate modeler in the audience, they'll know that this is a very big jump. And then we test our same statistical emulators on a very warm simulation. In my case, I'm mostly showing neural networks trained on aquaplanet simulation, although we also have prototype in realistic geography settings. Our aquaplanet simulations use the fixed prescribed surface temperature. And in the cold climate, here is a surface temperature profile we impose as a function of latitude on the x-axis. And here you can visualize how the warm climate compares to the cold climate. And you can see that there's an entire region, an entire latitude band, where the neural network is going to be exposed to surface temperatures it has never been trained on. It's trained in the cold climate, and then we are going to test it on purpose in the deep tropics of our warm climate to make sure it fails as much as possible. So here it is. We take a daily mean tropical prediction in the cold climate. We make sure that our neural network is a good fit in the reference climate. Otherwise, if it's a bad fit, we know why it doesn't generalize well. But if it's a good fit, then we have isolated the failure mode due to the generalization error. So again, we take a tropical profile in the warm climate, and we reevaluate the same network I just showed you, and it fails miserably. And because of the 8 Kelvin jump, it fails by more than a factor 10. So now, how can we solve this problem? Our idea, which was inspired from the self-similarity properties in fluid dynamics, was to physically rescale the data to convert an extrapolation problem into an interpolation problem. So if we mathematically look at the mapping we're trying to emulate from the large-scale thermodynamic vertical profiles to the response of clouds and convection to those large-scale thermodynamic conditions, what I've just shown you confirms that if you fit a neural network, just a typical neural network quickly, this mapping that is trying to emulate is not climate invariant. You cannot use the same function in the cold and in the warm climate. And our hope, if there is some degree of self-similarity in how convection responds to thermodynamics from the cold to the warm climate, is that we can rescale the input vector, the output vector, and the vertical coordinate so that this mapping becomes climate invariant. And we can use the same mapping in the cold and the warm climate. And now I'm going to show you how to choose this physical rescaling. And there's not a single solution, but I'm going to show you how to choose it from 3 different perspectives. So first, from a physical perspective, why does the machine learning algorithm fail when we warm the climate? From analyzing the data of our aquaplanet simulation, more specifically binning the near surface specific humidity on the near surface temperature, we can see that the atmosphere becomes moister as climate warms. And then if we take a simulation that's 4 Kelvin warmer, we see that it doesn't become linearly moisture, it becomes exponentially moisture as the surface temperature warm. And that is due to Clausius-Clapeyron equation that dictates that the maximal specific humidity that the atmosphere can contain before water vapor condenses into liquid and ice water is a roughly exponential function of temperature and a function of pressure. But here we work at mostly fixed vertical pressure levels, and we can mostly focus on the temperature variations. And it is this exponential dependence that makes it so hard for the statistical emulator to generalize to a warm climate. For instance, if you were just looking at the blue curve and guessing how it would continue as the climate warms, you could guess this direction, you could guess this direction from this data, and both directions would be wrong, but could be reasonable fit in the cold climate. However, once you know the upper bound, you're much better off. It's much easier to guess how this full line is going to vary given how the dotted line increases with surface temperature. And so our idea is to use this upper bound to help the neural network extrapolate. For example, instead of directly predicting specific humidity, we're going to normalize it using saturation-specific humidity, which yields a relative humidity. So now I'm going to take a different perspective. Imagine you were not a physicist. From a statistical perspective, we have an extrapolation problem. If you look at the specific humidity distribution in the cold climate, it doesn't really go above 18 grams per kilogram. Now, in the warm climate, the neural network is quickly exposed to specific humidity values that can be as high as almost 30 grams per kilogram. Meanwhile, if you normalize specific humidity by saturation specific humidity and look at the relative humidity distribution, now you're much closer to an interpolation problem where the normalized distribution, the normalized histogram, which is a proxy for the probability density function, are much more aligned across the two climates. Now, the final perspective is from an algorithm perspective. How do you quickly test and implement it? So what we have developed is that you can implement those rescalings I mentioned before using custom data generators and custom layers. And without going into details, by implementing it using the statistical emulator itself rather than rescaling all of your data, you can use only one training, validation, and test data to test multiple rescalings quickly, which is important because it's really hard. It's not trivial to find the best physical rescaling, or at least one that works at to a satisfactory degree given how hard the problem is. And we do that via data analysis and trial and error. And then we keep the rescalings that yields the best generalization. For instance, if you switch from specific humidity to relative humidity, you get predictions that are not perfect, but they're better than by a factor at least 5 compared to our brute force predictions. And so to summarize what we have done so far, we have physically rescaled the inputs so that the probability density function of inputs were as aligned as possible across climates. And that results in climate invariant neural networks that generalize to climate they have never been trained on. Taking a step back, the specific result is consistent with a broader consensus in the literature that using machine learning to intentionally phrase machine learning mappings can dramatically improve performance, often more so than carefully tuning your algorithm or choosing a given algorithm in particular. And that underlies how important it is that domain knowledge experts and computational experts work closely together whenever they are to develop new statistical emulators of physical systems. Now, I want to quickly finish by coming back to the last problem, the fact that observations of convection are sparse. Sorry. And how we can and how the field in general is trying to get around that problem by using what we call transfer learning, which can be summarized as a reuse of a pre-trained model to a new problem. And we'll give a more concrete examples right after. In climate science, one logical application of transfer learning is to go from climate model data, which we can output as arbitrarily high spatiotemporal frequency with perfect labels, to sparse observational data. A recent example from Hamital shows that by first training a convolutional neural network on idealized climate model data and then fine-tuning it in observational data, it was able to yield predictions that were much more consistent with observations. And because we are always limited in terms of observation, what we have developed in our lab is a numerical laboratory to investigate the amount of data needed to transfer knowledge from idealized to realistic atmospheric data. So we train neural networks on our idealized aquaplanet data before unfreezing and then retraining all their weights on more realistic atmospheric data. So from a machine learning perspective, we're doing what we call inductive transfer learning, as we retrain our aquaplanet neural networks on labeled data from a closely related task. And this setup is quite naive, as we're not freezing particular parameters of our neural network, and we're not changing the learning rate. So the results I'm about to show you are very preliminary, yet promising. So when we use transfer learning from the aquaplanet, it's a real geography simulation with the mean squared error on the y-axis and the x-axis being the number of samples used from the real geography data set that we used to retrain an algorithm that was trained on the aquaplanet data set. What our preliminary results suggest is that not only does the climate invariant, the rescaled network I introduced earlier, network perform better on data sets with very different characteristics without any retraining, without any data. So just from the get-go, it performs better on data sets that are quite different. It is also able to learn better from less data. So in conclusion, what I showed today is that we can make neural networks model of convection more physically consistent and trustworthy by first tailoring machine learning interpretability methods for the particular purpose of emulating physical process. We can enforce physical constraints approximately in the loss function or exactly by changing the architecture of the neural network. We can help neural networks generalize by physically rescaling inputs and outputs, and the resulting climate invariant neural networks learn more general mappings and facilitate transfer learning. And one aspect I find particularly exciting is the idea that physics-guided machine learning may be one of our most promising tools not to replace data assimilation, but to assist data assimilation by assimilating very sparse data from observational field campaigns into global climate models in a way that's physically consistent. And before I finish, I want to use the last 2 minutes to make the point that all the work I presented above was about incorporating physics into machine learning models of convection, while an exciting scientific endeavor is to also go the other way around and extract physical knowledge from data using machine learning. And so I'll advertise recent results from Griffin Moores, a very talented PhD student in our group, who from high-resolution vertical velocity data derives the latent space you see on the top left using unsupervised learning, and more precisely, a statistically constrained variational autoencoder. And note that the clustering we get via this unsupervised learning method is more compact and informative than the clustering you would get from more traditional methods, such as principal component analysis or linear models. And with that, I'll finish my talk. I linked my research website at the top of this slide if you're ever interested in the details or the open source code of any of the projects I discussed today. Thank you again, and I would be happy to take questions.
Thanks, Tom. So we have 10 minutes for questions. So feel free to use the raise hand option in the chat. If you go to the participants view right at the bottom of the name of attendees, you'll see the option to raise your hand. I actually don't see that option myself. I was expecting to see it. So let me try another thing. Just feel free to unmute yourself and go for it.
Well, how do I raise it?
Okay, I'll read a question from the chat. John Patterson's asking, can you give some other examples of input rescaling besides specific humidity to relative humidity?
Yes. So, sorry, I'm gonna. Okay, let me see if I can find the corresponding slide. Okay, so well, maybe I'll answer the question directly. So we in the end we have to rescale all of the inputs here so that they tend to vary less with climate, and we have we had initial success. So the specific humidity is the most dramatic successful input rescaling we've obtained. But by just subtracting the near surface temperature to temperature, we had some promising result. And then we developed other results by, for instance, normalizing the temperature by using the near surface temperature and a fixed tropopause temperature assumption, which holds well as the troposphere, so that the temperature is always 1 at the surface and 0 at the tropopause. In general, there's no need to rescale surface pressure and solar insolation, and those are, as well as sensible heat flux, as those are relatively climate invariant. And then you can use near surface specific humidity or variance of this quantity to rescale latent heat flux. So those are a successful input rescaling so far. In terms of vertical coordinate rescaling, since the atmosphere tends to shift upwards with warming, because the temperature of the tropopause is relatively fixed across climate, its pressure tends to go down. We playing with different vertical coordinates that ensure that the tropopause is always at the same level. Those are a few examples. Does that start answering the question?
Yeah, thanks very much.
I can see a raised hand from Juno.
Yeah, hi. It's actually not Juno, it's Francois. We're watching together. But yeah, I have a question. In your constrained neural networks, you impose some conservation properties. And if I understand correctly, you have like a global conservation of mass or humidity or something like that. Have you thought of maybe putting in like the parent model, the model you trained it with is also a bunch of conservation laws. So could you put in even more constraints on that output, that last layer, so that you could constrain maybe a coarse grain version of your original model so that you would do even better? I mean, is that an avenue for doing better? So you'd have your neural network and then your layer where you put your constraints would be a coarse grain version of the original model. So you'd have not just global, but local conservations.
Yeah, that makes sense. That's a really good question, and it's related to how you formulate the mapping to begin with. So in our case, we formulate the mapping locally in space and time, and what that means is from a vertically resolved thermodynamic profile, we predict a vertically resolved response. And because of that structure, the conservation properties you can enforce are related to column conservation properties. Now, if you think of the detailed model, and what we're getting at is that in the end, it integrates vertically resolved conservation properties as well that operate in the horizontal dimension. And so in our case, we cannot, because you take a single column as an input and a single column of the output, we don't have information about the neighbors. So we are unable to enforce anything else than the 4 conservation constraints. But that would be different if, for example, you had a 3-dimensional convolutional neural network that would take several columns next to each other. And in the limit where you take all the column, you could also impose, for example, a horizontally and vertically resolved 3-dimensional quartz grains conservation laws, as you were getting at. But that's a trade-off because our parameterization is more simple and we get more training data by defining it locally. And as you say, you could put more constraints if you use the entire data, but then you get much bigger neural networks that are much harder to train and you get much fewer samples. Does that answer the question, or is there still?
Yeah.
So,
thank you.
Yeah, I would recommend like a few really good fluid dynamics paper where they can it's much lower dimensional, and so they can add almost all the constraints in the neural network, and then they can get the better results for less data, etc. But in climate modeling, it's just so much harder because we have such a high dimensional system.
Mm-hmm. Thank you.
Galen, would you like to unmute yourself and ask a question?
Yes, hi, thanks for the talk. It's really great. I have kind of a 2-part question, and feel free to answer just one if you want. But this is sort of a follow-up to the physical rescaling you were talking about. You said you were using these conversion layers kind of at the front and the back of the, I don't know, meat of the neural network. And I was just curious, are those parts of the network, are those sort of layers part of the network itself, or are they pre-processing and post-processing steps? And then,
oh, sorry.
No, just the second part is just, when you said you kind of search for the best ones, how do you perform that search?
Okay, so there's those are 2 excellent questions, and the answers are very different. So for the first one, the answer is yes. Either via the custom data generators and custom layers, we can directly implement in TensorFlow, because TensorFlow is a relatively flexible language, and so we're able to, for example, encode the conservation of mass in TensorFlow. And since all of our code is open source, I can point you to the repository and where it's implemented. And so that's taking advantage of the fact that now TensorFlow is not too much harder from more classical libraries such as NumPy. It's definitely harder, but it's feasible. So we can enforce them exactly with either in the data generators or custom layers. Or you can also code custom loss function with the same idea. And then for the second question, so how do we typically measure which fit is best? So usually we use in general, we would use a performance metric, as you're familiar with, so mean squared error, and to select the best network, if you're more from the machine learning perspective, you're going to try to find the best hyperparameters of your model. For example, if you have formal hyperparameter tuning, which our lab has a lot of recent work on. But then from the more particular perspective of this physical rescaling problem, you're really trying to do a combination of physics and statistics. And so you really have to look at the system from every angle. And the reason I chose the vertical profile of at the tropics is because it was a good compromise between looking at the samples that are the most problematic, but also having enough samples to average over the noise. But I don't have a single answer yet, and we're developing fun statistical method to do it offline by seeing if we can statistically distinguish samples from the cold and the warm climate, or looking at different performance metrics. In general, I would say that's very much work in progress, and I wouldn't be surprised if we find something that's even easier than the way we're doing it now.
Thanks so much.
Thanks to everyone for your time and interactions. I see we're at 2 o'clock now, so let's thank Tom once more, and hope you all have a great afternoon. Thanks, Tom.
Yeah, thank you, Mike. Thank you, Alex. Thank you, Elliot, and thank you to everyone who attended.